Yes. So hello everyone. So basically, this kind of funny image will pave the way of this presentation, which is gonna deal with a new geocentric approach to recalculate trajectories based on survey stations. So it introduces like a hierarchy on a CRS coordinate reference system, but it's a joke. So let's go ahead. So I'm Arthur de Calan, author in English. I've been working with Denis Reynaud and Ludovic Macrezi at Path Control Paris offices. So we are providing services of expertise in survey management, but also relief wells, ranging. We have patented the passive magnetic ranging technology. Before that, in my early life, I used to work in Brazil in autonomous, remote autonomous systems, and I'm graduated from both azimuth tech and a Masters of Robotics and Autonomous Systems in Colombia. All right. So in this presentation, we'll introduce first to neophytes what is basically geodesy and why it is relevant in the context of directional drilling. We'll talk about the conventional projection method, which is the conventional way in which softwares recalculate trajectories. And we will introduce a new method, which I call the geocentric method. So I have to give credits to two previous presentations, which I didn't assist, unfortunately. Respectively, one made by Eric Marchand in Anchorage ITWA community, and one other made by Geomatic Solutions in Stavanger, both dealing with geocentric data as a way to unify different data of different fields. All right. So first, let's introduce what is a coordinate reference system. So basically, it's a theoretical object which is composed of two objects, a datum and a coordinate system. Basically, a datum is what ties the coordinate system to the ground. For instance, we can take the example of WGS 84, which is the main ellipsoid used in projected coordinate systems that many people in directional drilling are using. On the other hand, you have a coordinate system which basically describes how the coordinates are associated to a point. So you have basically, you have more than that, but we can define three types of coordinate reference system. The first one is the map, or projected, which is defined by its coordinate northeast vertical. There is another one which is geographic, or also called geodetic, defined by latitude, longitude, and elevation above or below the ellipsoid. And you have also the ECEF, Earth-centered, Earth-fixed reference systems, defined by central points, often the center of gravity of the Earth, and X, Y, Z coordinate system. So, for instance, the EPSG 4326 is a composition of both objects. These are keywords and remarks about geodesy. Maybe we won't describe all, but the main information here that we have to remind is that in this presentation, we are about to make coordinate conversions and transformations from one CRS to another. And what is important to note is that what we call coordinate transformation is absolutely not the same thing as coordinate conversion. There is a difference there. So if I employ the transformation term instead of conversion, I always mean conversion. So transformation is basically an empiric way of changing a coordinate in a certain coordinate reference system from one datum to another, instead of conversion, which is the change of a coordinate from one coordinate systems to another coordinate system, but within the same datum, and that's the important thing here, which is much more accurate than the transformation. What is exactly what I call the conventional projection method? Basically, when we are working on a map, so defined by northeast and vertical CRS, we have to introduce some distortion factors that comes from the fact that the Earth is not flat. I guess that in this room, a few people are flat earther theorists, and well, maybe Chris D'Souza from NASA is not. So basically, we have three types of distortion factors. In fact, if we are precise, we have more, but for our purpose, it's sufficient to mention those three. The first one is the areal scale factor or surface scale factor. The second one is the meridian convergence, the deflection of the grid azimuth toward the true azimuth, which depends both of these distortion factors depends on the surface location you are considering on a given coordinate reference system. And the third one do not depend on the horizontal location, but depend on the depth you are. So it is the elevation scale factor. And to illustrate it, I represented three lines, and you see that both blue lines, when projected on the red lines, which is the line describing the curve of the ellipsoid in your coordinate reference system, they have their length change. So when it's above the ellipsoid, the elevation scale factor is negative, below 1, sorry. And when it's below the ellipsoid, the elevation scale factor is more than 1. All right. So how do we reconstruct a trajectory based on certain inputs? So let's start with a simple example. You have A and B points defined by their service stations. So major depth, inclination, azimuths, and you have A position in northeast vertical reference system. The first thing you do is applying convergence. It depends on what type of azimuth you have. If you have true, you convert your azimuth into grid to work in a northeast vertical reference system. Then what you do is building the point B based on A with a minimum curvature algorithm, which is described by these assumptions. And then you can apply, and then you have to apply distortion factors only on the horizontal departures. So first the surface scale factor, and if you want, you can apply also the elevation scale factor. And I'll explain after why I say eventually. And then you have B points in a northeast vertical coordinate reference system, and you have all your trajectory. You apply it consecutively until the bottom hole of your well. So I distinguish here two manners of doing this simple algorithm. First one is the global manner, in which you only consider one pair of one batch of factors. It's usually the factors defined at the surface coordinates of your wellbore. And for the elevation scale factor, you often define it as 1 or an average value. But you can refine this algorithm by doing a kind of local projection method, in which you do not use distortion factors taken at the surface location of your wellbore, but you recalculate it at each point so that you get a kind of discrete evolution of convergence scale factors, surface scale factors, and elevation scale factors throughout the trajectory until bottom hole. We won't discuss this second algorithm, but it's much more precise than the first one, especially in places where the distortion factors gradients is important. Okay, so this is just the more refined flowchart of both algorithms. So what we can say is that this first method, whether it be global or local projection method, may introduce some approximations due to the fact that the Earth is not flat and that we consider, on the first hand, concerning the global projection method, that the surface distortion is uniform, which is false because it evolves throughout the horizontal well path and the vertical displacement. You have also an error due to the fact that that there is reflection in the vertical vector, so it's the elevation scale factor effect. If you consider only one throughout the trajectory, you make a mistake. Similar to the, and you have the similar approximation for local projection method. And one other approximation what you are making here, but which is common to both algorithms, that you are considering that the most probable well path reconstruction between two consecutive survey stations is the minimum curvature. Okay, based on those approximations, let's try to build another method that's kind of wiped out of those approximations that I mentioned, except the minimum curvature algorithm, and that would give eventually better results. So how do we build a point in 3D space based on geocentric method? So we start from the same input as we have to adapt to the inputs given by the drillers. So we have A coordinates given in a certain projected coordinate reference system of an UTM. Survey at point A, survey at point B. We are in northeast vertical. First operation is converting inclination and azimuth of points A and point B into unitary tangential vectors in A and B, as the first one, in fact, as the first method. And here's the trick. What we do here is basically converting both points, like absolute coordinates, point A, into a geocentric reference system, providing coordinate conversion, and also converting tangents in point A and point B, expressed in NEV, into XYZ, providing its latitude and longitude and rotation matrix. So we get it. And what we do here is performing once again the minimum curvature algorithm in order to build the delta dx, dy, dz between A and B. Then we can reconstruct point B based on this shape from point A, given that we have the A coordinates in the geocentric CRS. And then, if we want to communicate back with drillers, we have to convert back. So do the opposite coordinate conversion from XYZ to NEV. And that's it. So it's as simple as that for now. Let's assess this method with a scenario that I built. Basically, in this scenario, we will imagine that we have a path from A to B that is following exactly the curvature of the Earth. So it's a horizontal well path. We could say it's not so well bored because it's fully horizontal. So it's theoretical. We start from A, and we will build a source of truth, which is the point B, given by the direct Vincenzi formula, which is basically the direct Vincenzi formula is given an input, so measured a length along the ellipsoid and a forward azimuth defined in A, we can build the coordinates of B exactly following the curve of the ellipsoid. So we build this point, and you can see that there is an artistic view at the right side with B following exactly the curve in 3 dimensions. So you have the assumption of this scenario at the bottom. Then what we do is, once we have built point B by the Vincenzi direct geodetic problem, what we do is building C with the conventional manner or the projecting manner. So insofar as we we are in a horizontal well path, and we are using global convergence both in A and B. What we can say is that we are not applying any minimum curvature algorithm here, given that A and C are collinear. But we still apply surface scale factor on AC departure, which is 2000 meter, to get C position. So I represented both B points and C points in the right side. It's like mathematically incorrect, but it's a way to figure out what I'm talking about. So we get 2 points, B and C. And then the third one would be the point D, this time defined with a geocentric algorithm. So here you have the same assumption, both for point C, D, and B. B points built with the Vincenzi formula, direct formula, C point with conventional formula, and geocentric points, D points with geocentric formula. And we get a 3D shift computed in north-east vertical between B and D and B and C. First, the departure between B and D is almost zero. It's like 10 to the power -5 meters. So it's almost zero. And the cool thing is that here we can question ourselves, why is there this tiny error? Basically, the minimum curvature algorithm in XYZ between A and D, minimum curvature algorithm is following the path of the surface of a sphere. Instead of the Vincenzi formula is not following this well path, it's following the path of the surface of an ellipsoid. So we can suggest that this tiny error of 10 to the power -5 is due to the fact that we are not following an ellipsoid path, but a sphere path in the geocentric method. And you can see that we have a shift between the conventional manner and the conventional points, conventional C points, and the Vincenzi B points, which is our source of truth. And one thing also important to mention is that here we do have, for the geocentric algorithm, we do have minimum curvature, even though it is an horizontal well path, given that we convert A tangents and D tangents into a XYZ coordinate reference system. We have a tiny curvature, which is almost the local curvature of the ellipsoid. All right, let's move on. We'll try here to extend the scenario, the horizontal scenario, to any scenario. So here is a simple example. We have no more source of truth given by the direct geodetic problem, direct Vincenzi problem, but at least we can build and calculate the absolute bottom hole shift given by the geocentric method compared to the conventional method. So first we built it with a conventional manner, point B, and then with a geocentric manner, point C. And we can have a 72 centimeter shift over a 3,000 meter measured depth along this well path composed on only 2 points, which remains theoretical. Then let's move on to a real case. So I faked the surface location for confidentiality purposes. Basically, we have a real relief well scenario in which I'm sorry for the color, which are not matching neither in the left, in the center, in the upside of the slide. Sorry, but basically you have a relief well intercepting the offset well at a certain depth. So I did not plot the table of the survey, but basically you have inclination azimuth here. You can see that it's about 3,500 meter depth, measured depth. And so in this scenario, I plotted 2 things. First, so along the well path, you have here the minimum center to center given at each reference survey station from the different at each surface station of the relief well compared to the offset well. Both curves of center to center are combined for now, but you can see that we have a shift in the center to center from both methods, which is varying, but there's not any pattern for now. There's not any tendency. It may not depend. It may depend on the measured depth. It may depend on other factors. We don't know. But basically, let's zoom in to see what it looks like with a more refined measured depth window, and we can see that there is a shift, which magnitude is about 40 centimeters in bottom hole, which for a relief well operation is kind of significant. But we have to always to compare that to the error model given by the sensors, which is another matter that we can discuss in the question. All right. So basically, to compare both approaches, it's basically the same core concept in which we try to rebuild trajectory based on surface stations and curvature minimum. But the shift is that we are applying it in a northeast vertical reference system on the one hand, and on the second hand on a XYZ reference system. The main approximation that we are making in the conventional manner is that we are considering at a certain stage that minimum curvature is applied as in the Cartesian space, because we apply it in a northeast vertical reference system, which is kind of inaccurate because minimum curvature is only valid mathematically in a Cartesian space, which is much more accurate in XYZ CRS. We have specific error sources coming from the conventional method that we already mentioned, and we have specific error sources coming from the geocentric method. We are tied to the precision of the CRS conversion when we convert tangents and points from and to an EV and XYZ. And we are also tied to the precision of the datum grids, if applicable. Why datum grids? Because we always are relative to the ellipsoid height, but it's not always the reference elevation we have when we are dealing with northeast vertical surface coordinates. We often have the mean sea level, the elevation relative to mean sea level or to rotary table. And so what we can do to enhance this, to avoid this specific error source is applying the shift between the mean sea level reference and the ellipsoid reference. So to wipe out another issue caused by the fact that we have not the height above the ellipsoid, but above the mean sea level or below. And so the common error sources remains, and so it's still the fact that the minimum curvature algorithm is considered the most probable well path. So we identified, well, now that Ildiko made a presentation on the today, it's maybe not an error source. It's more like we identified an error in the methodology of trajectory calculus. We have to put in perspective the fact that the shift introduced by this change in method is not necessarily significant compared to global error model like gyro or MWD. Moreover, we have not set the pattern of how is evolving the bottom hole, the absolute coordinate shift when we are using a geocentric method rather than an EV method. So it's unclear. It may be measured depth, maybe surface location relative to the CRS we are in. It may be the well path profile. whether it is vertical, whether it is toward west, north, whether it is horizontal. We have some elements, but we cannot conclude on the model. And in the end, we can eventually enhance this method by providing dynamic CRS such as WGS84 and accounting for coordinate epoch management. In case you have tectonic motions between the moment you acquire data and the moment you calculate the trajectory based on that data you acquire. Okay, so the way forward, what is it? The first complicated approach is to ask all software developers to maybe include it into their softwares, but it's a kind of idealistic way forward. So the most probable discussion we can have is whether we can include this error source in the error model, the existing error model. And so we can discuss this in because I know that the error model is kind of limited in terms of because you have to express the error sources in terms of inclination and azimuth, which in this case does not fit. And thank you very much for attending this presentation.
Questions, anybody? Adrian?
The comparison that you have the slides, I think 3 slides. So yeah, here, yeah. I was expecting the shift to accumulate, but since they happened with the first data point and then stay there, please write the difference between the blue and the orange.
Sorry, I'm not sure to understand everything you said.
Here you're comparing the 2 methods.
Yes, I did.
So the shift happened right away at the beginning. I thought this would accumulate over.
It doesn't. It doesn't. As you can see, if it were okay, so this scenario is a specific scenario, as it is a center-to-center comparison between the conventional manner, like both and the geocentric manner. So your question is, it's an opportunity for me to show a scenario that I built in the appendix of this presentation. Here it is. Here we are not comparing the standard to center in collision avoidance or interception scenario, but only the shift in bottom hole between both. So when you say it accumulates, not necessarily. In some cases, yes. In some cases, no. There is no pattern. For instance, for the ISWA well bores, so I made the calculus for the ISWA well bores. So the first one is kind of long in terms of measured depth, and you have a shift in a 3D shift in bottom hole of 5 meters over 8,000 meter. But in the case of ISWA 2 and 3, we have a much. You can see that measured depth is not proportional. Is not proportional to the shift you can the error source in bottom hole. So there is a kind of, you could say based on that, okay, there is isolated linearity if you make the calculus on one well or another. But if you shift the coordinate location or the well path profile, the angles or the measured depth, you will see that there is not linearity on the measured depth. For instance, if you are making let's imagine a circular well path, I don't know. Does it answer your question or not? Like there is no pattern that allows to determine the error introduced by the fact of not using geodesy in the calculus.
Is there a interval at which this one parameter will reduce the distance between points it the one good? Will this be a problem?
Sorry.
Do we have improvement or this will eliminate?
So the first part of the question, sorry. It's my English.
You have very tightly spaced surveys. Would that improve it, or would the error still be there?
Good question. No, no, it's not related. You mean if the server sampling changes, does it affect the bottom hole location?
No.
So instead of 100-foot between surveys, it's maybe 1 foot between surveys. 10
Yeah, so it's the server sampling, basically server sampling rate. Yeah. I said no, but it is worth to make an assessment of this. I've not been so far in the interpretation of the results.
All right. One more, and then we got to move on.
The agenda. Hello.
But it seems very similar. We have adopted that in software, it's just that none of us ever use it. And one of the reasons people are scared of it is there's all sorts of other software that does well investment. Geological sites, they have so you're kind of pushing against you.
Yeah.
Question. Was the previous paper published by Wilson and Williams?
Yeah, I guess that's applying this consideration in trajectory calculus may be a source of fear among the software producers. The idea here is to come with another time with a debate subject about whether it is relevant, especially in whether it is relevant to continue with the way we calculate trajectory. Moreover, there are places in the Earth, especially on the poles, where distortion is very high, and where you may not apply I only stayed with the realistic scenario cases. I didn't pick super high or low latitude, or even next to CRS bounds, everything. And so you may have big issues when you try to calculate on a conventional manner trajectory that are far from CRS conventional coordinates.
We have it on there. Yeah. All right. Thank you again. Good.
You're welcome.